line spectra in the Bohr model, atomic emission spectra, most sources produce light that contains many wavelengths at once. However, light emitted from pure substances may contain only a few specific wavelengths of light, called a line spectrum, as opposed to a continuous spectrum, like the rainbow is a continuous spectrum. You get a continuous spectrum from a prism. With these pure substances, they only give off very specific colors. So sodium gives off a yellow color when it is electrified or charged. Hydrogen, on the other hand, when it is electrically charged, will give off 4 different specific colors. Niels Bohr theorized that electrons travel in certain orbits around the nucleus, or they only have certain stable distances from the nucleus that they like to stay in. You used to learn the Bohr model had like these rings around the nucleus. That is true in the sense of energy. Each electron will be in a certain energy level, which is a certain distance from the nucleus. But that does not mean those electrons stay in very specific circular paths around the nucleus. If the electron did not stay in this specific energy level, the electron would emit or lose energy, slow down, and eventually crash into the nucleus. We can figure out the orbital energies with this equation. We've got the principal quantum numbers, which is the main energy levels, 1, 2, 3, 4, and Rydberg's constant, which is given to you there. Now, the 2.178 times 10 to the negative 18th, that's just Planck's constant times the speed of light times Rydberg's constant. Since they're all constants, you can multiply them together and get this 2.178 times 10 to the negative 18th. Here's a picture of increasing energies. If you start at level 1, in order to get to 2, you would need to absorb energy. And in order to get to 3, you would need to absorb more energy. So as n approaches infinity, or as your energy levels get greater, the electron is essentially removed from the atom and the energy will become 0. Once the electron gets too far away from the nucleus, it will not have anything really holding it to the electron. So as the energy levels get bigger, the electron gets further and further away from the nucleus and eventually will not have anything holding it to the atom. Ground state is the lowest energy level in which an electron is stable, and the excited state is any energy level higher than an electron's ground state. So I look at it as us sleeping, we're in our ground state. We're using the least amount of energy. And when we're awake, moving around, walking, talking, we're excited state because we're using more energy than we would if we were sleeping.
According to the Bohr model, when a hydrogen atom receives energy, its electron leaps from a low-energy orbit to a higher one, forming an excited state. As the atom loses energy, the electron jumps back to a lower energy orbit, releasing light as it goes. When gaining energy, the orbit to which the electron jumps depends on the amount of energy involved. When the electron occupies the lowest energy orbit possible, the atom is said to be in the ground state.
In this experiment, we are going to look at the characteristic colors given to flames by alkali metal compounds. The first flame is the red flame caused by lithium. Lithium chloride on a platinum wire gives a red flame when inserted into a Bunsen burner flame. Next, sodium chloride. Sodium chloride is placed on the platinum wire. It gives a characteristic yellow color when placed in the Bunsen flame. These colors can be used to qualitatively identify the presence of the metals. A yellow flame always indicates the presence of sodium. Finally, potassium chloride. Potassium chloride on platinum wire is placed in the flame, and it gives the characteristic lilac color. All these colors arise because the alkali metal atoms are raised to excited states by the temperature of the flame, and then return to the ground state, emitting light of a characteristic frequency.
Here is an equation that allows us to use Rydberg's constant and the beginning and end energy levels of an electron to find out its energy. If we take this equation and plug it into our previous equation with frequency and Planck's constant, we can determine the frequency of energy based on where it started and where it ended in terms of orbitals and the energy that was absorbed. Now this third equation, all this is the second equation rewritten with the negative from the second equation distributed to the quantity. So the quantity inside is flipped around on the third equation if you take a look at that. And I'll point this out in class. Here we can look at a line series depending on where the electron begins or where it moves to will determine the type of electromagnetic radiation given off or taken in. So if it starts or ends at level 1, it is ultraviolet radiation. If it starts or ends at level 2, it's the visible spectrum. If it starts or ends at energy level 3, we're looking at infrared. And if it starts or ends at level 4, we're looking at the very far infrared part of the spectrum. And each of these series are named after the scientists that determined and discovered them. So taking a qualitative look at it all, if a light that corresponds to the transition of an electron from n equals 4 to n equals 2 state of the hydrogen atom is the light absorbed or emitted. When we start at 4 and we go to 2, in order to drop energy levels, we need to drop energy or release energy. So if energy is released, we're emitting energy. The other way around is if we start at a lower energy level and jump up, we have to take on energy to jump up to those higher energy levels. So energy is taken in or absorbed in this instance. Matter is a wave. Planck said that energy, we can use that and it can be determined by the speed of light and the wavelength. Einstein said that energy will equal the mass times the speed of light squared. And de Broglie said that if both of these scientists were correct, then we can have both equations equal each other, and we can simplify it down. Therefore, if the particles have a mass, then they have an associated wavelength. We are also able to say that the waves with a wavelength have an associated mass and velocity. So any wave will have a mass and velocity to it as well. Let's practice. What is the characteristic wavelength of an electron with a velocity of 5.97 times 10 to the 6 meters per second? If we know the mass of an electron is 9.11 times 10 to the negative 28 grams. Well, here we have our given, our velocity, and our mass of electron. We don't want our mass of electron in grams, we want it in kilograms. So we're going to convert that over. You'll notice our exponent changes. We're looking for wavelength. We know our constant, our Planck's constant, but we want to get rid of the joules and have a kilogram meter squared per second square in there. So we're going to plug that in, simplify our unit for our Planck's constant because we're dealing with mass. Using our new equation from our previous slide, we can plug in our information, our Planck's constant with our simplified unit, our mass of an electron, and our velocity, and find that our wavelength is 1.22 times 10 to the negative 10th meters. Heisenberg's uncertainty principle states that it's completely impossible to determine the exact position and exact momentum of an electron. The reason is that in order for us to determine the position of an electron, you have to detect how light reflects off of it. But light means that you're going to be exposing the electron to photons, and that's energy. So when the photons strike an electron, the energy is going to cause the electron to change its motion and therefore its momentum. So electrons cannot be moving in well-defined circular orbits around the nucleus. Electrons are constantly emitting and absorbing different amounts of energy, and because of this, it will change their location and their momentum in the atom. So we can never know both.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom. which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
All right, we are going to end our video there. I've included little video clips throughout the notes to help you kind of understand bits and pieces. When we begin next, we're going to start here talking about electron density and then move on to quantum mechanics.